Hi, I'm Toru Tanzawa. I'm going to talk about the tutorial on the clocked AC/DC charge pump. This work is based on these publications. Let's get started. This slide shows the background of this work. We have the energy harvesting technology for IoT sensors. One application is like this. So, so aiming at the autonomous sensing for safer society. This is an example for the bridges. The sensors are attached to the bridges, and vibration is continuously monitored. Alarm is triggered in case of abnormal vibration, indicating a potential collapse. So before potential collapse, the check is triggered to prevent a major accident. So this is one example for the sensor module. This vibrator indicates, in this case, a bridge. So bridge is vibrate, and the energy transducer is attached. So this device output power, electrical power, uh, by inputting in from the vibrator, uh, and the output of the energy transducer is alternate current. However, the sensor module needs DC voltage. As a result, we must have AC/DC voltage converters between the two. The design goal is the integrating this AC/DC converter into the Sense IC to reduce form factor and cost, contributing to the spread of battery-free IoT sensor network. There are several devices for vibration energy transducer: piezoelectric, electrostatic, magnetostrictive devices. And these are the characteristics, electrical parameters for each the technology. The output impedance, output voltage, output power density. So as you see, the magnetostrictive device has the highest output power density. This means that the device size can be significantly reduced from the alternatives. However, this device output voltage is lower than the voltage that the sensor requires. And also the output impedance of this device is much lower than the alternatives. And then, therefore, this work aims to propose a compact AC/DC converter for the magnetostrictive energy transducer with low output voltage and low output impedance. Using the following two slides, I'll show the previous works for AC/DC converter. The one example is the AC/DC charge pump. And here's a charge pump circuit composed of multiple capacitors and diodes connected in series between the input from the energy harvester to the output, the sensor or RF ICs. The fundamental operation principle will be explained later. But on this page, I just want to show how you can increase the output power is simply increase the capacitor every stage capacitor, because the operation frequency is determined by energy transducer, which is particularly much lower than megahertz, say 100 hertz. 100 hertz. If you want to have the, say, 10 microwatt, every capacitor requires 1 nanofarad. This means that those capacitors must be discrete capacitors, resulting in a large module size and production cost. So this was the problem that we want to resolve. Second previous work is AC-DC and DC-DC conversion. So we have the judgment here because we want to integrate every component in chip. And a charge pump is considered the input voltage is DC, and that clock is generated by on-chip oscillator like this. And because the input is AC and we want to the DC voltage here, therefore AC-DC conversion is realized by using full bridge rectifier followed by a diode, another rectifier, to make this output node is DC. In this case, you must have the very large the filtering capacitance here, which should be off chip. And before moving forward, I would like to show the fundamental the performance limit of AC-DC charge pump. In this example, for simplicity, I show the two-stage AC-DC charge pump circuit. We have two phases, the up terminal plus and or minus. So one cycle composed of two phases, and these two phases are repeated. And in the first phase, the charge are transferred from the power supply to the first capacitor through first diode, because this node is go high and this node is go low. And at the same time, the third diode also transfer the charge because this node goes up high. And in the second phase, the second diode conduct because this node go high and this node go low. And by repeating these two operations, the power input from the energy harvester to the charge pump can transfer to the output terminal. Then this node voltage is boosted. The key thing is the output current is proportional to operation frequency times stage capacitor C, because the If you increase the frequency, the total amount of charges in 1 second is doubled when the frequency is doubled. And also, if you increase the capacity, stage capacitor twice larger, then the charge transfer every cycle increased by a factor of 2, resulting in I out is proportional to frequency and also capacity. So question is the fundamental frequency of the vibration energy transducer is very low, meaning F is very small. So we want to have certain amount of the current, say microamps or more, and then C must be very large, resulting in the discrete capacitors, meaning the module size of the AC/DC charge pump was very huge. So this is the problem we want to resolve. Then here's the concept of clocked AC/DC charge pump. What's the difference is that if you increase the frequency, then the capacitor size can be reduced to get the same amount of I out. If you reduce the capacitor size so that all the components can be integrated into a small silicon area. So in order to increase the frequency F, you just put the oscillator, on-chip oscillator, and original rectified the signal is makes the can have these shapes. It is not easy. It is not difficult to realize the on-chip oscillator over 1 MHz. This number is several orders of magnitude larger than the original frequency. So this is a concept. The following several slides, I'll show how the circuit can be modeled. This is the original the input power or voltage sinusoid, whose frequency is Fin. And through on-chip oscillator, the CLK, which drives the charge pump, has the shape of this. And the frequency of the clock is FCLK. When the amplitude is greater than certain voltage, then output current should be appear like this. As the clock amplitude increases, the output current also increases like this. Let's define theta S, meaning a starting phase with theta S. Here's the original DC charge pump output current versus output voltage relationship. These equations can be shown the previous publications, and these components, VTH effective and total output resistance, is given by these equations. By the definition, the theta s is uh, like a I out becomes zero, and so that you can solve the equation for theta s like this. And then our I out suffix k, meaning uh, the meaning the k equal 1 indicate the very first output current here. Using this relationship, this is defines the k actually. K is the wave number starting from theta s. This equation indicates that at the kth average output current can be calculated by this equation. Then our interest is overall average output current over one cycle. We just need the average current using this formula. And this is a very useful formula to calculate our case and input this I out k with this equation given in the previous slide, and using this formula we get the average output current. It can be calculated by these parameters. We also want to know the average input power to calculate the the power efficiency. The input current from energy harvester is estimated by this equation. This is also given in the previous publications. And using this equation, the average input current over one cycle is also given by this. Average input power should be calculated by this equation, and we already know the ICP theta, and then this integral can be executed like this. As a result, once you get the number theta s, then actually the average input power can be calculated with this equation. Because our V out is about DC voltage once the system enters in the steady state, then average output power can be calculated by this equation. So to validate those models, equations, and the effectiveness of clocked AC/DC charge pump, and we designed and fabricated this circuit. Here's the vibration energy harvester side, and the other part is the clocked AC/DC charge pump. The clocked AC/DC charge pump is composed of full bridge rectifier, the two NMOS and the two PMOS makes the uh, full bridge rectified, meaning input sinusoid can be output to this shape. And this shape is provided to on-chip ring oscillator. And because we want to validate the frequency dependency, and then therefore the voltage controlled oscillator is designed. And so this circuit, by changing the V control from external, the current can be modulated, and then the oscillators runs at 1 to 10 megahertz. And this the charge pump side, we determine the number of stage and the capacitor per stage like this. And here's the additional the equations to estimate total input power, composed of the charge pump power for this part, and oscillator power here, and P off. The P off is because these transistors have the low VT transistor. As a result, when the input side is below inside voltage, then potentially there is a reverse leakage. So this contributes to additional input power, and therefore the total input power can be calculated by this equation. We should have the power efficiency in a two folds. One is the eta total defined by P out divided by P total, like this. So this means that the clocked AC DC charge pumps power efficiency. So input power versus output power. Another definition of power efficiency is the relative to the available power from energy transducer. So this power is the maximum number when the vibration energy transducer is connected to the same impedance of the output impedance of the vibration energy transducer. We call it as eta system. This is a diphoto of that circuit. Here's the charge pump circuit, and major component is capacitor, and minor component is the diode. And this portion is the incurs full bridge rectifier plus oscillator. And we have 5 paths to measure the circuit performance. Ground, the V leg is just for monitor. V out, we connect the filtering capacitor and the variable resistor. And being V2, V1 and V2 is connected to vibration energy transducer like this. And another, of course, we have the VCTRL somewhere here. and to control the clock frequency. So this is a measured result. Say the original the experiment, the AC voltage source plus the resistor connected like this, and here's the V1 minus V2 here, meaning the voltage amplitude is 0.5 volt. This green curve shows the V leg here, and this color shows the internal clock. So if you zoom up, then this clock looks like this. In this example, the clock frequency was the 4.8 megahertz, and this is the input versus output. So 0.5 volt amplitude is boosted up to DC 2 volt. Here's the measured comparison between the measured and simulation and model. Where the so this is common experiment conditions. Here's the clock frequency versus output current. So this bold curve showed from the model equation, and also the measured point and simulated points are also plotted. So as the clock frequency increases, then output current also increase. So up to 10 megahertz should be good enough for this design. And this graph shows the clock frequency versus input power. And input power is also these are the breakdowns of the input power. Based on the estimate. This bold line shows the total power calculated by the previous equation 14, which has the three components: PCP, POSC, and POFF. Let's look at this. This is PCP, which basically is proportional to I out. This straight line shows the POFF, and this line shows the POSC. So when the input clock is very low, much lower than say 100k kilohertz, then the input power is majority of the input power is P off. Over 1 megahertz, the majority of input power is the PCP. Below 10 megahertz, 100 megahertz. In this design, the POSC is the minor. And also the measured and simulated total power is about the same as the model calculations. Power efficiency, the measured and spice result are lower than the estimate by equation 15. Probably we need further analysis this discrepancy. This is measured at the output voltage versus output current with the different input voltage amplitude. And this is the input voltage amplitude versus output current. Input voltage, input power versus available input power versus power efficiency. So the either this is total power efficiency is about 10% or lower. The breakdown is also uh, analyzed in the later slide. This is very unique. The characteristic output current under this condition is not dependent on the input frequency, clock frequency, the frequency of vibration energy transmission. So this means that the once you get the unified design, that design is also applied, can be applied to any the energy transducer which has the different the frequency. So this is unlike the previous the AC DC charge pump, which has a significant frequency dependence on the I out, because I out is proportional to Fe. But this in this the clock AC DC charge pump, I out is basically determined by input on chip the ring oscillator frequency rather than Fe. So universal design is can be used. And we also validate the circuit with real magneto-selective energy transducer from Renault lab. The magneto-selective device is put on the vibrator here, that one, and the vibrator can change the frequency and also acceleration. This graph shows the device alone characteristic. And in this example, this energy harvester has the resonant frequency around 195 Hz with 0.5 G. This is gravity acceleration, and the voltage amplitude is increased as the vibration acceleration increase. This is the waveform with the different resistor, load resistor directly connected to energy harvester. For example, when you provide a 0.5 G at 195 Hz with the 1 kHz ohm, then your amplitude is about 0.5 volt. And this is a measured spice and model result with the real magneto-selective vibration energy transducer. Output current with the different acceleration were matched, and it is a single curve from measured result, meaning input voltage at the input of the judge pump and output current from the judge pump is about the linear increase as vibration acceleration. The following a few slides, I compared the clocked AC/DC judge pump with other designs, and this slide compares with the AC/DC judge pump. We also implemented the AC/DC judge pump without oscillator, ring oscillator, whose the silicon size is same as the clocked AC/DC judge pump. With the same condition, the output current versus output voltage is significantly degraded from the clocked AC/DC judge pump case. And because the output current is on order of 10 nanoamp, and also output voltage cannot go higher than 0.3 volt. If you get the same the output current about the several microwatt at output terminal, the AC/DC judge pump requires a discrete capacitor like this, and total 10 capacitors requires the 1.5 centimeters squared. And with the clocked AC/DC charge pump, AC/DC charge pump and the clocked AC/DC charge pump, these two have the same output power, but 1,500 times size difference. So this is a very critical effectiveness of the clocked AC/DC charge pump. This is a breakdown of power. The upper side shows the AC/DC charge pump with 3 nanofarad capacitor, and the below one is the clocked AC/DC charge pump with 10 picofarad capacitor size. And to have about the same output power of 4 microwatt, then the available power of 63 microwatt and total input power of 9 microwatt input to charge pump, and charge pump has the power loss of 5 microwatt, resulting in the output power of 4 microwatt. The remaining the 54 microwatt is reactive power, meaning the input power is reflected to the energy transducer side. And below side, because the higher frequency than the above, then input power can be increased here. But because of the high frequency, the power loss is higher than the above. However, because the input power is higher than the above, and resulting in the same output power. So this means that both sides, ether system is the same, but the ether CP is different. So as long as the ether system is equivalent, the power efficiency is the same, with the over 3 orders magnitude size reduction with the clock DC judgment. So this is a comparison with another design SDC, DC charge pump. We should have the two alternatives for AC/DC conversion using passive diode or active diode. So active diode has the negligible small the voltage drop through the switch. The passive diode requires additional voltage overhead, but the active diode is much lower than passive diode at the sacrifice of additional power for this gate control. And this the estimation we use the 1 microwatt. This is a comparison between the clocked AC/DC charge pump and AC/DC charge pump with passive diode. AC/DC charge pump required a filtering capacitance at the rectifier node. In this example, the 500 nanofarad, meaning this capacitor should be external. Because of this voltage drop, the clocked AC/DC charge pump has the higher out current at a certain output voltage than AC/DC charge pump. This graph shows the comparison between the clocked AC/DC charge pump and AC/DC charge pump with passive diode or active diode, like this. So cold start, meaning the starting point to get finite I out. The passive diode requires additional voltage than active diode or clocked AC/DC, and therefore the cold start point is higher than the others. However, once because this active diode cannot operate at cold start because you don't have any power at the output terminal, meaning this detector doesn't work at cold start. So even though you have the active diode, you must also have the passive diode in parallel with the active diode. So when the cold start, the power must flow through passive diode. And once the output terminal goes high, so that this detector can work, and then it has the characteristic. So let's think about the input voltage first increase once greater than 0.5 volt or higher, and then the power pass can be switched to active diode. So this characteristic can be switched to this card. The clocked AC/DC charge pump can operate uh, with the lower cold stat like this. Here's the input voltage versus power efficiency, eta total between the three cases. Because no additional component for clocked AC/DC charge pump, and then power efficiency can be high when the input voltage is low. At the high input voltage is high, then the because the B deck is DC to high voltage than the clocked AC/DC charge pump, therefore power efficiency can be larger. This the table compares other designs, and EM indicate electromagnetic vibration energy transducer. Of course, the physics is different from magneto-restrictive, but in terms of the output impedance and output voltage, the characteristics are about the same. Here's the comparison, the discrete element and the values. And here's the circuit area and the maximum F win. And here's the power efficiency. Because the power efficiency is significant dependence on the input voltage, output power, and therefore it is not easy to the fair comparison. But the so probably this number is a constant for now. We should improve the power efficiency of clocked AC/DC charge pump. In summary, we proposed the fully integrated clocked AC/DC charge pump. The idea is increasing the frequency with an on-chip oscillator, increase the output power of the charge pump. So instead of increasing the output power, we can reduce the circuit size. The factor was 3 orders. And using the actual device of magneto-restrictive vibration energy transducer, we successfully convert output power of 4 microwatt at 2 volt using the 0.11 millimeter squared. So this indicates that the clocked AC/DC charge pump can be integrated into IoT chips for vibration energy harvesting. And the very unique the thing is the universal design, meaning the circuit has the negligibly small dependency of output power on the frequency of the vibration energy transducer. So this is also reduce the total cost, including the design and fabrication of the chip. Uh, so that's it. Thank you.